Hello everybody, welcome to Function Operations. Today we're going to learn how to perform operations such as add, subtract, multiply, and divide, real functions to solve real world problems, and we are going to use compositions of functions to solve real world problems. Alright, so let's just start with adding and subtracting. So first we're going to add and subtract functions, and then we're going to talk about how those relate to the domain of those functions. So if we have f of x equals 3x plus 4, and we have g of x equals x squared minus 5x plus 2, what is f plus g of x? Well, it's just f of x plus g of x. So in other words, if I have 3x plus 4, and then I add g of x, which I'm just going to kind of write this like this, x squared minus 5x plus 2, we add these together, and we get x squared minus 2x plus 6. Okay? Now let's look at g minus f of x. Well, it's kind of the same idea, right? It's going to be g of x, which is x squared minus 5x plus 2. And then it's minus f, right? So it's the opposite of x. So if x was 3x plus 4, this is going to be negative 3x minus 4, right? We take the negative of that. And now we just kind of add down, right? So it'd be x squared minus 8x minus 2. All right, so how do the domains compare? Well, let's go ahead and take a look at a graph real quick. So what I have here is I have 3x plus 4. 3x plus 4 is this red graph, right? It's just a line. You guys should know this. And then we have x squared plus 5x plus 2. It's a second degree function, so it should form a parabola, which in this case it does. Now, you'll notice that the domain of the parabola and the domain of the line are all real numbers, because every x value is going to work for both of these functions, which means that the domain of the combined function is also going to be all real numbers. Okay? But that's it. If they're both all real numbers, okay, that doesn't really answer a lot of questions, right? So how do the domains actually compare? Well, let's take a look at a couple of domains that we know don't cover all real numbers. Or let's look at one that does cover all real numbers and one that doesn't to see how it works, okay? So let's look at this, right? We have the square root of x, which we know looks like this, right? It kind of comes up a little bit and then it kind of squares off. We know that this will never go into the negatives for x, right? It's x is greater than or equal to 0. Now, we know x is a straight line, right? A straight line that will go from negative infinity to positive infinity for both our x and y values, right? Our domain and range. So this would be x, right? Y equals x. Now, if we add the square root of x and x, we're just going to get the square root of x plus x. There's nothing more we can do with this, right? Well, what happens when we add the square root of x plus x? Well, we learned this yesterday when we did transformations, right? It's going to raise our square root of x graph up by x units, right? So I'll go ahead and graph this just to show you, right? You'll notice that it actually scales at a rate of x as it increases the square root of x, right? They're added together, which is kind of the idea. Now, you'll notice that the domain here, it stops at, well, it's x is greater than 0, right? So it's actually the same as this domain. And you'll notice that this domain is the restrictive domain, right? This domain is all real numbers, right? Our purple graph here, y equals x, is all real numbers. So our more restrictive domain ends up being the domain of our black graph here, which is the square root of x plus x. What this means, and maybe you'll remember this term from geometry, I went ahead and drew the little picture for you. Do you remember in Venn diagrams, we had multiple things, right? One of these things was known as an intersection. And an intersection was a combination of sets where all of the parts were shared by both sets. And then we wrote the intersection in this form here. It looks like P, and then what looks like the top of a capital A without the little line, and then Q. And this meant P and Q. And what that means is that it's sharing the contents that both have, right? So if we go back to the graph, just to kind of explain this a little bit, right? The y equals x covers everything, right? This graph here only contains the part where x is positive, which means the only parts in the domain that are shared are the positive parts, right? So in other words, the more restrictive piece is the one that's going to control the domain, right? That's known as the intersection of the sets. And in this case, it's the intersection of the domains, right? So when we look at the domain of functions that we've added together and subtracted, it is going to be the intersection of those domains. In other words, whichever one's the more restrictive is the one that we're going to take as the actual domain of the new function that we created after adding or subtracting them. Just a little fun piece to know. All right, so now let's multiply functions, and let's do an application problem at the same time. The reason why we're just going to do this at the same time is because, honestly, I've said this in the past, but when you start to get into higher levels of math, multiplying and dividing are almost always easier than actually adding and subtracting, because there's a lot more we can do with multiplying and dividing. So let's just kind of do a problem as we go, and I think you guys will get the gist of this. All right, so the demand that we're calling D of X in units sold for a company's new brand of cell phone at price X in dollars is listed below. The cost, C of X, to manufacture the cell phone is also listed below. What is the company's expected profit from cell phone sales in terms of X? Well, first of all, I went ahead and we have the D of X here, right? And of course, D of X is our units sold, right? It's the demand, right? In units sold, where units sold is X, right? Our cost is C of X, which is here, which is the 2200 plus 80X. And then, of course, our price, right, is just going to be X, which is the price per unit, right? So we can even write that, right? The price is just X, right? And everything's in terms of this price. All right, well, we're trying to multiply and add these functions, right? Because we have profit equals price times demand minus cost. So let's just put in the stuff we know, right? The profit is the thing we don't know, right? So I'm just going to kind of say like equals, right? We can just leave this kind of blank. We can even say like big P of X or something, and we can call this profit if we want to. It doesn't really matter. And this equals the price, which we determined is X, times demand. So times the demand was 5,000 minus 10X. And then minus our cost. So minus our cost, which is 2,200 plus 80X. And you'll see that now that we kind of understand how multiplying or adding and subtracting works, you kind of see that multiplying is just going to work the exact same way. We're just kind of taking the functions that we have and we're just applying the operation of multiplication to them, right? So in other words, the first thing we're going to do is here we have X times all of this and then minus all of this, right? And we're going to multiply before we subtract. It's order of operations, right? So what we're going to have is P of X equals 5,000X minus 10X squared, right? All it is multiply both of these pieces by X. I distributed. Okay, and then minus, now remember this negative is like a -1 and it also distributes. So negative 2,200 and then negative 80X. And now we just have a bunch of things we're subtracting, so we can just combine like terms, right? So P of X equals, let's start with our X squared. So negative 10X squared. I see a 5,000X and a minus 80X. So we can just kind of subtract those two, and we will get 5,000 minus 80 would be 4,920, right? So plus 4,920X. And then we have just this negative 2,200, so minus 2,200. All right. And this is our profit, right, as of the price times the demand minus the cost. Now, remember that our domain is the intersection of all of these terms, right? So if we look at this one, this here, 5,000 minus 10X, that's going to be a straight line, right? X is a straight line. 2,200 plus 80X is also a straight line, right? So in this case, the demand would be effectively all real numbers, right? But if you look at if you think about what the question is asking, right? Can the profit be negative? Well, yeah, in this case it can, right? So you should always ask yourself, practically speaking, should I restrict the domain, right? And in this case, you don't really need to, because profit theoretically could be negative, right? And in this case, it actually looks like, depending on how many they sell, it actually could be. Which makes sense, right? You have to sell so many before you're going to make money. All right, so dividing functions. Let's go and move on to the next piece, because we've kind of really said everything about that we can. Dividing functions, as you can imagine, works exactly like multiplying functions would, right? With one small difference that has to do with the domain, okay? And that's always going to be true. Every time we have variables in the denominator, we're always going to have to think, how does this affect my domain, okay? So let's do this. So we have we're finding f divided by g of x, where f of x is x minus 7, and g of x is 2x squared minus 13x minus 7. All right, so let's go ahead and find our quotient here. So this is going to be f over g of x, so x minus 7 over 2x squared minus 13x minus 7. And now what's cool is we get to kind of play around a little bit with something we haven't used in a little while, right? We're going to use our little tree. And remember that we have to take AC, so this is negative 14. And then over here we have negative 13, right? This is A times C. In other words, 2 times negative 7 is negative 14. And then this is just our B, right? And now we have to say what multiplies to get negative 14 that adds to get negative 13, right? And the answer is negative 14 and 1, right? So we have a negative 14 over here. We have a positive 1 over here. Negative 14 times positive 1 is negative 14, so we're good. And then negative 14 times, or plus 1 is negative 13. So these are the numbers we need, right? And so what we're going to do is, remember, we have to break this apart, right? The negative 13 is going to split up. So this is going to become 2x squared minus 14x plus 1x, right? This is where this 14 and this 1 come into play. And then minus 7. And now we're going to factor by grouping. So we're going to combine those and combine those. If you didn't remember this trick, it's kind of why we're redoing it a little bit. All right, so we have, let's take out a 2x from this side. So now we're going to have x minus 7. And then over here, we already have x minus 7, right? So we're just going to take out a 1, which is essentially not taking anything out, right? And then x minus 7 over here as well. Now we have the two terms that are shared, which is what they should be, right? So you'll get 2x plus 1 times x minus 7. And now we can actually look at the original, right? So now all we've done is factor this bottom piece. So now we'll have, and I'll just kind of like write this over here, we have x minus 7 over 2x plus 1 times x minus 7. And the x minus 7s will cancel, right? So that we'll get 1 over 2x plus 1. All right. So this is our final answer, right? This is f divided by g of x, right? This is all we did is just divide the two numbers, right? So what's the domain? So let's kind of think about this, right? First of all, f of x, originally x minus 7, this up here, that's just a line that's shifted down 7, right? This is 2x squared minus 13x minus 7. This is just a parabola, right? Both of which will have all real numbers as their, they'll always have all real numbers as their domain. Now, there are going to be a specific set of restrictions anytime we have variables in the denominator, right? So let's take a look at this. If we actually look at this, right, we have an x minus 7 up top and an x minus 7 on the bottom, and we eliminated those, right? And then what we did is we went back up here, right? And, well, we were left, I should say, with the 2x minus 1, right? So what is the domain? Remember that we have to use this part here, right? Because both of these cannot equal 0. The 2x minus 1 cannot equal 0, and the x minus 7 cannot equal 0. So 2x plus 1 cannot equal 0, right? And x minus 7 cannot equal 0. So what does this mean? Well, x cannot equal, if we add 7 to both sides, is 7, right? And then over here, x cannot equal, subtract 1 divided by 2, negative 1/2. Right? So every other piece of this domain is perfectly fine, right? Except for where x equals negative 1/2 and where x equals 7. And if you plug this into your graph, that's what you'll see as well. Actually, one of them will be a hole, right? Because it's eliminated from top and bottom. And the other one would be an asymptote. Hopefully you remember that as well. All right, so that's dividing, right? We essentially are literally just taking f of x and g of x and just doing what it tells us. All right, so we've learned how to add, subtract, multiply, and divide. We can kind of cross off learning objective number 1, right? We performed all 4 operations to functions, and it occurs the exact way you'd think it would. All right, now composite functions can be a little bit tricky, but they're really not too bad. It's more or less the way it looks makes it look more tricky than it actually is, sort of thing. All right, so let's just take a few assumptions here. If f of x is x squared, and g of x is x plus 1, so two pretty basic functions, a basic parabola, and then a line that's been translated up 1, right? So we're going to find f of g of x, and this can also be written over here like this, right? F of g of x is the same as this f of g of x. You'll notice the circle is not colored in. I tried my best to show that it's a circle without making it look like an O, right? But essentially what this is, if you want to think of it like this, right? If I like zoomed in, this would be like f of g, right? It would be like this, okay? So it's actually like an open circle. And what that means is that we're essentially going to take g of x first, right? Figure out what that is, and then we're going to take f of that solution. And I know this sounds kind of confusing at first, but let's just do a problem and you'll see what I mean, okay? So remember how I said we have to do g of x first, right? Well, we know what g of x is, right? We can substitute this in. G of x is x minus 1, right? So if I'm finding f of x plus 1, right? Well, what we're going to do is we're just going to plug in x plus 1 wherever we have x, right? Because if we look up here, we say f of x equals x squared. So what we're going to do for f of x plus 1 is this is going to equal x plus 1 squared, right? Everywhere we have an x, we're going to substitute it with an x plus 1, right? And now, I mean, you can FOIL this out if you want to, right? This would just be x plus 1 times x plus 1, which is, hopefully you remember this little pattern. This is going to be x squared plus 2x plus 1. And that's it, right? This is what f of g of x would be, right? So first we found g of x, because the g is closest to the x. That's usually the way I remember it, right? Even in both situations, that's true, right? Like this g is right next to this x, and this g is next to the x. So you take the one closer to the x. G of x is just x plus 1, right? So g of x is just going to be whatever g of x is, which in this case we said was x plus 1. And then what we're going to do is we're going to take f of the value of g of x, which in this case is x plus 1. When we take f of x plus 1, right, remember that f of x equals x squared. So everywhere we see an x, think of it as like you're substituting that in for this x right here, right? So f of x plus 1 is going to be f of x plus 1 squared. And then all we did is FOIL, right? If you want to actually take some time and FOIL that out, you can. But just, you can kind of trust me on this. That is the FOILed version. All right, so let's go ahead and try this, okay? I know that I went through that relatively quickly, but this is just going to be one of those things you have to practice a few times and then it'll kind of click, okay? You're essentially just substituting numbers in. So let's go down here to the try it, all right? I'll give you guys a chance here. We're going to find f of g of 2, right? So we're going to substitute a 2 in for x this time, right? First for g. And then we're going to find f of g of x. Feel free to do this in either order. The one we did before was more like the second part. But honestly, the first part when you have a number is a little bit easier because it's going to pop out a number as an answer. Okay? So go ahead and try both. Pause the video, do the work, and when you're ready, unpause the video and we'll see how you did. All right, so let's go ahead and find f of g of 2 first, right? In other words, we're going to find g of 2 first. Well, if I plug in, if I'm looking for g of 2, you'll notice that everywhere we had an x, we're now going to have a 2. So this is going to equal 3 times 2, which is simply 6. So g of 2 is 6, right? Now we have to find f of g of 2, and g of 2 is 6. So we have to find f of 6, right? And remember that if we're just substituting this 6 in for x, this is going to equal 2 times 6 minus 1. 2 times 6 is 12, minus 1 is 11. So f of 6 is 11. So f of g of 2 equals 11, right? So if we start with the number, we're essentially just substituting numbers in for the x's all over the place until we get down to the number at the end. All right, so f of g of x. So this is a little bit trickier, right? Because g of x, if we're substituting an x in for g of x, well, we're not really substituting anything in, right? X is just x. There's nothing being transformed by this x except for multiplying it by 3, which is what the function already tells us is going on anyway. So g of x, in this case, I'll kind of separate this. G of x equals 3x, right? So what is f of g of x, right? Well, if g of x equals 3x, then we can say f of 3x, right, equals, and now everywhere we would have an x, we're going to replace that with a 3x. So now we're going to have 2 times 3x minus 1, right? 2 times 3x is 6x. So f of g of x equals 6x minus 1. That's it. That's all you can really do. But this is what's known as a composition, right? I tried to give you kind of more basic ones just to start off. Obviously, these can get very, very complex, and the more problems you do, the better, okay? Actually, let's go ahead and jump into an application of one. And what's awesome about this application is you really don't even have to know anything about math to be able to solve this, right? But I'm going to show you how you can use an application, or how you can use these composition functions that I just showed you, right? I'm going to show you how we can use these to solve these kinds of problems. All right, so a clothing store is offering multiple discounts to their customers. The customer can apply the discounts in any order they wish. In which order should the customers apply the discounts to maximize their savings? Well, if you know anything about discounts, well, first of all, most places don't let you stack coupons anymore, right? But if they did let you stack coupons and you have one that gives you a certain number off, right? This gives you $10 off. This gives you 20% off. You should always take the percentage off first because you're going to take a percentage of a larger number, right? And when you take the percentage of a larger number, it's going to give you more of a discount. And then you take off the value that's not going to change, aka the $10, right? So we should already know before we even jump into this problem that we should take the 10% off before the $5, right? That's just kind of a little bit of common sense. If you don't, if that doesn't make a lot of sense to you, well, I'm going to show you mathematically how that makes sense, okay? So if we think of f of x, right? In other words, our original discount, f of x, is just going to be the cost, right? If we let x equal the cost, right? Well, then what would f of x be, right? F of x is going to be our cost minus $5, right? Make sense? Okay. So now we're going to have g of x, and g of x is going to be our second coupon here, right? 10% off your next purchase. And if we think about what g of x is, if we're taking 10% off of our purchase, we're paying 90% for the item, right? So I'm just going to put this as 0.9x, right? There's probably a couple ways you could do this, right? You could probably look at this as g of x minus 0.1x or something like that, right? There's probably a bunch of ways you could do it, but this makes logical sense to me, right? We're paying 90% of x now. Okay. Now, what we want to know is we really want to know, okay, well, which one of these is going to be better for us, right? Well, let's find f of g of x, and let's find g of f of x, and see which of these looks like it's going to give us a better deal, right? So let's start off with g of x f of g of x, right? G of x is 0.9, right? So let's say 0.9. Right? And then, so this is g of x, which we already knew, right? So g of x is 0.9, and then we are taking f of g of x, right? So anywhere we have an x, we're going to take f of g of x, which was 0.9x, right? And that's going to give us 0.9x, right, minus 5. So this is f of g of x, right? This is if first we take the 10% off, right? G of x, we take the 10% off first, and then we take the $5 off afterward, right? Well, let's look at it the other way. What if we take g of f of x? Well, we can say that this would be f of x, which is x minus 5, right? So what we're going to find is g of x minus 5, right? And if we go here, this was 0.9 times x minus 5, right? And now we can actually distribute this. So this is gonna equal 0.9x minus, and then this would be what, 4.5, right? Okay, perfect. So this is pretty easy to compare, right? The first set of discounts, when we do f of g of x, means we're taking the 10% off first, right? When you take the 10% off first, you're gonna get 0.9x minus $5, right? Whereas if you take g of f of x, in other words, you take the static discount, the $5 off, if you take the $5 off first, you're going to get 0.9x minus 4.5. So here, you're getting all $5, right? What's happening is if you do the $5 first and then you take the percentage, you're actually losing 10% of your $5 off, right? So you're actually losing that 50%, which, like I explained, that's the way it should work, right? You should always you're trying to maximize your discount, so you're going to take the percentage of the higher value. That just makes sense. All right. So what did we do? Well, first of all, we talked about performing operations, add, subtract, multiply, and divide. And we learned that we kind of just add, subtract, multiply, and divide. There's not really much more to it, right? When it comes to the domains, we're finding the intersection of the domains. In other words, which one is the most restricted of the domains. And then the other thing to consider is when we're dividing functions, just like always, because we have variables in the denominator, we have to account for that. So in this case, we solved for it, right? We got the 1 over 2x plus 1, and then we figured out that x could not equal -1/2 or 7. And then when it comes to composite functions, right, this is, again, I would just recommend practicing these. The more you see them, the more you'll kind of get it. But it's essentially just substituting things in, right? So here we'll have f of g of x, right? And we know that g of x was x plus 1, so we're going to find f of x plus 1, right? And because this was just x squared, it's going to be this is going to equal x plus 1 squared. And then we did the application where I got to teach you how to stack coupons if you ever get a chance to do that. So, awesome. All right, well, that's it. I'll see you in the next video.